So this video is going to be about the vapor compression cycles. And here is the problem statement, the TS diagram, and the diagram here. And you can see there's 4 states. So to organize my code, I'm just going to write out all the states. Up top, I'm just going to comment a title and do vapor compression cycle. Calculate solve. Comments are normally blue, but if you put an exclamation point, you can make them red. You can also edit them in options, but we're not going to do that. So the givens is just that the low and high pressure are set to 140 kilopascals and 80 kilopascals respectively. So low pressure would be the evaporator, so that's state 1 and state 4. So I'll write P1 equals 140 kilopascals and P4 equals P1. Then the high pressure of the condensers, state 2 and state 3. You see here's the pressure line of high pressure, 800 kilopascals. P2 equals 800 kilopascals. P3 equals P2. Here we know at state 3 the working fluid is a saturated liquid. So at state 3 we put quality equals 0, and then I'll just comment saturated liquid. At state 1, another given, saturated vapor is the working fluid at state 1. Do quality state 1 equals 1. I could put here sat vape. Okay, and then you know if you have 2 independent properties, you can find the rest of them. So here at state 1 we have pressure and quality. We could do options, function info, thermophysical properties. The working fluid is some sort of refrigerant. I'm just going to assume the refrigerant you're using is R134A. I don't see it specified in the problem statement. No. Okay. So I'm going to assume it's just R134A. Then I'm in real fluids. Going to do real thermoprops, pressure, and quality are my independent properties. Paste. Here's the colon. The colon separates independent input values from the output values. So to the left of the colon are input values. We have our working fluid and our 2 independent properties. To the right of the colon we have our output values. So if you didn't want to find all these, let's say you just want to find temperature, you could delete all these and just find temperature as the output. And I'm going to write in 1 for the arrays. And then ease doesn't recognize lowercase and capital letters, so even though quality array 1 is lowercase here, and here I specified it as capital letter, it doesn't make a difference. So we know state 3, we have 2 independent properties, so you can find the rest. Options, function info, thermophysical properties, real fluids, refrigerant 134A, real thermal props. Here we have pressure and quality. Paste. Element 3 in the arrays. Okay. Now we need one more independent property to solve state 2, one more independent property to solve state 4. If we look from state 1 to state 2, this is a compressor, and it looks like we're assuming the compressor is isentropic. So state 1 S equals state 2 S, the entropy. So we can write S2 equals S1. And now we have two independent properties, and we can solve the rest. It's going to go options, function info, thermophysical properties, real fluids, R134A, real thermal props. Our independent properties are pressure and specific entropy. Paste. Then we'll make sure we write in the correct array values. Okay. Now our last state to define is state 4. Oh, and also just a good point is, where do we find state 1? We found state 1 as our output here for a real thermal props function. So we're going to do something similar to state 4. See, state 3 to state 4 is an expansion valve. And expansion valves, the enthalpy is constant. So specific enthalpy is constant. So H4 equals H3. Now we have two independent properties, and we can calculate the rest. Options, function info, thermophysical properties, real fluids, refrigerant 134A, real thermal props. Now we have pressure and specific enthalpy. We'll paste. Then we need to fill in the variables. 4. Okay. Now we found all our thermophysical property values at every state. Compute the coefficients of performance and total heat absorbed by these cycles. Okay, so I went through Dr. Donnie's lecture slides, and I found the coefficient of performance equation. So we'll comment COP, and we'll do eta equals H1 minus H4 divided by H2 parentheses H2 minus H4. I'm not going to do eta. Not efficiency, sorry. Just make the variable COP. We can also do the Carnot COP. So I'll do this. Carnot equals TC, I set compressor temperature, or sorry, condenser temperature is state 3 and state 2, so I could put either or. So I'll do T3, or is it cold? Sorry, no. Alright, so Carnot coefficient of performance is the cold temperature divided by the hot temperature minus the cold temperature. So cold is evaporator, so that's state 1 or state 4. So we'll do T1 divided by T3 minus T1. So it would be the Carnot coefficient of performance. And total heat absorbed by these cycles. So the heat into the system is from the evaporator, because it's taking heat. That's why the cold refrigerant base is cold. It's removing heat from it. So we'll just put that down there. So we'll do Q in, heat into the system, equals, I believe it's H1 minus H4. Now we can expand this. Oh shoot. I'm going to minimize it again real quick. Oh, okay. Never mind for the Carnot, because that's not the hot and cold region. Like, T1 equals T4, but T2 does not equal T3. These aren't the temperatures of the hot region. Just going to delete this line of code. To calculate, solve. This equation is unmatched brackets. I have an extra square bracket that I'll delete. Calculate, solve. Okay. So the COP is 79.87%, and heat into the system is 143.7 kilojoules per kilograms. Here we have an array table of our thermophysical properties at every state. So there's state 1, 2, 3, 4. If you want to right click, you can specify the units. Here it's degrees Celsius. Here you can also add Fahrenheit if you want to view it in the red. So here you can see the temperature in Celsius, temperature in Fahrenheit. We already specified kilopascals in the code, that's why it came out like this. You can specify everything. Units would be kilojoules per kilogram. Meters cubed per kilogram. Kilojoules per kilogram. Kilojoules per kilogram times Kelvin. Okay, that's your array table. You can also, if you need to do work, copy and paste this into Excel, I believe. Do Control C, see if this works. Yeah. So if you want Excel table, you do that. Or you can right click this. First we can also just exit it out. Calculate, solve. I'll get my array table back. I'm going to right click and just, can I change the title? No, it's whatever. So save. Going to go to can save it as an Excel file, save, then I can go open it again, and here, instead of copy and pasting, gives me the units and the name of the columns. It's another way you can do it. And we can also make a property plot. So we do plots, property plot. You want to find your working fluid, so I'm looking for R134A. We can do, what does Dr. Donnie have? We're going to do a TS diagram. So we chose TS, and then we can choose our lines of pressure and specific volume. It's going to look here, 140. Here we have 800. Going to uncheck these. Then specific volume 0.1401, 0.02687, 8458, 0.04569. I can just change the color just to show you when it comes up. So I'll make pressure lines purple, specific volume lines yellow. I'll hit OK. Well, the yellow does not come out well, so don't choose yellow, but it's there. Then, now that I have the property plot, I need to overlay the TS arrays onto it. So the first one's going to be wrong, but I'll just show you. Plot, overlay plot, TS, R134A. Your x-axis is going to be S, Y is going to be T. You can make that orange. Here you can see that's not how it's supposed to look, but we can adjust this. So 1 is fine, 4 is fine, 3 is fine. But we need to make, first we need to connect 1 through 4. You can see there's no orange line connecting that. So I'll just show you how to fix that first. We're going to make an imaginary state 5 to connect 1 and 4. So we're going to make T5 equal T1, S5 equal S1. Calculate, solve, go to array table. We can do overlay plot again. Make this one red. ST, okay. Now you can see we have a complete cycle, but again we need that point. So we pull up this. We'll have to make an imaginary state here. And it will have the same temperature as 3, and it will have the quality of 1 because it will be a saturated vapor. So X will be 1, P will equal T. Temperature and pressure are the same, so we can just do temperature and pressure. Or we'll do quality. No, we need quality to specify. And what was that in between state 3 and state 2? So how do we want to make this? 1 goes to 2, 2 goes to 3, so 1. This will be our new state 3. And I'm going to make P3. We'll make T3 equal T4, and X of 3 will equal 1, because this is going to be a sat vapor. Now I'm just going to change these for the sake of the property plot. If you have like a project or a quiz, don't name the states wrong, but I'm just going to do this to complete the property plot. I'm going to name this state 5. Three is now 4. I'm going to rename this one state 6. And again, I'm just renaming these states so I can change the array table for the property plot. Like, don't call these states state 1 through state 6 anywhere else. It's just for the sake of creating this property plot with an ease. So I need to calculate this. Pressure is out of range. Let's see what state this is. We have state 1, 2, this is our new state 3. So it's saying this state is out of range. What card do I have? Okay, so now that we have our new array table, this can also show you a better look of how array tables work. So it's this new state 3 I have, I only specified temperature and quality. So here we have an element 3 in the temperature array, an element 3 for quality, but there's no state 3 for anything else specified. And same thing goes for our imaginary state 6. I'll do plots, overlay plot, ST, we'll make this one green, we'll make it dash lines, missing data row, oh I forgot to specify this, okay. Now that I have these two independent properties, I'm going to do options, function info, thermophysical properties. I only need entropy, it's going to be just redundant to do all this. You don't need all that information, so I'm going to find specific entropy. Entropy, we have temperature, quality, paste, I'll label this S3. Then we have TNS for state 6. Calculate, solve. You can see that we have entropy for state 3 now, which is that one extra equation we added, that function. Now I go to plots, overlay plot. We have all of our S's, all of our T's. We'll hit OK, and damn. So you see it did work. We added that extra. So if we look, we can adjust this. This is state 1, 2, 3, 4, 5. There's something wrong with state 6. Okay. I just had a typo. So state 6 equals state 1. Calculate, solve. Plots, overlay plot. I don't know, we'll make this one pink. S, T, and now it's correct. And you can, this is a good thing to see for overlay plots. You're just overlaying each plot on top of each other so it doesn't get rid of our error. You would have to create a new TS diagram, like how we had property plots. You would have to create a whole new property plot to just overlay one of them. And then I can zoom in to show you how state 1, state 2, creating this imaginary state 3 here allowed the property plot to look similar to the actual plot here. And I go back to the real one. Zoom. You can see state 1 to 2, then it goes to state 3, 4, and back to 1. If you want, I'll save the original plot. You can right click, save, file name, save. I can open up a Word document, insert pictures, this device. That's how you can paste your property plot into the Word document.